Welcome to systematic rhythm analysis, which will form the basis for analyzing basic ECG rhythms. This learning unit will introduce you to a 6 systematic step approach to analyzing basic ECG rhythms. We will also be looking at common concepts behind these steps as well as intervals and segments in ECG rhythms. The 6 systematic step approach involves asking the following 6 questions in a stepwise fashion for every rhythm strip you intend to analyze. The first question is the rhythm regular or irregular? The second question involves asking what the rate of the rhythm is. The method of measuring the rate will depend on whether the rhythm is regular or irregular, where we are interested to know if the rhythm is too fast, tachycardia, or too slow, bradycardia. Question 3. Are there P waves and what are the characteristics of these P waves across the rhythm strip? Rhythms originating from above the ventricles will demonstrate different characteristics of P waves. Question 4. Is the QRS wide or narrow? Narrow QRS complexes tells us that the rhythm is most likely originating from above the ventricles, for example, from the SA node, the atria, and the AV node. Widened QRS complexes, on the other hand, are propagated by the ventricles or may indicate aberrant conduction. Question 5. What is the relationship of P to QRS? Under normal circumstances, P waves precedes each QRS complex. However, AV node dysfunctions such as that seen in heart blocks may cause some intermittent missed beats. Question 6. What is the PR interval, which are commonly prolonged in heart blocks? It is important that all the 6 questions are answered before you come to a conclusion on an interpretation of a rhythm. Before we move any further, it is worthwhile to make sense of the ECG thermal recording paper where the rhythm will be etched on. If you look closely, you will notice that the graph paper consists of big squares and small squares. Each big square is 5 mm in height and 5 mm in length. Each large square is further subdivided into small squares, which measure 1 mm in height and 1 mm in length. The ECG is basically a plot of voltage on the vertical axis against time on the horizontal axis. Each small vertical square indicates 0.1 millivolts. The ECG paper ordinarily moves through the machine at a speed of 25 mm per second. However, you should take note that the paper speed setting can be manually changed on an ECG machine. 5 large squares are covered within 1 second, and therefore 1 large square will equal the time of 0.20 seconds. 300 large squares, on the other hand, will indicate a 1-minute strip. 1 small square represents 0.04 seconds. Thus, the number of R waves in 300 large squares will equal the heart rate in beats per minute. A 6-second strip consists of 30 large squares. To answer the first question on regularity, you will need to determine regularity of the heartbeat. To determine ventricular regularity, measure the distance between 2 consecutive R waves. This is known as an R to R interval. If the distance is equal throughout the rhythm strip, this is a regular rhythm. However, if the distance varies between R to R, the rhythm is irregular. To determine atrial regularity, on the other hand, you would measure the P to P interval instead. To determine rhythm regularity, you can use either the caliper method or the paper method. To use the caliper method, open the calipers to mark 2 R waves. You would then move the calipers down the strip to the consecutive R wave. At every point, you should determine if the R to R intervals are of the same length as the previous. If they are across the strip, then this rhythm is regular. The easier and more practical method for determining rhythm regularity is by using the paper method. Mark the R to R intervals on the edge of a blank paper. Then, move the marks along the strip to determine if the subsequent R wave falls regularly on the marking which you have made. If they do, then this rhythm is regular. The method of calculating heart rate on a rhythm strip differs depending on the regularity of the rhythm. For regular rhythms, where the R to R interval are equal throughout the strip, the number of R waves within a 1-minute strip, which consists of 300 big boxes or 1,500 small boxes, can be estimated by means of the 300 and 1,500 formula respectively. To use the big boxes to estimate heart rate, first, identify 2 R waves which fall as nicely as possible between a set number of full, large boxes. Mark those R waves by drawing a line extending upwards. Now, count the number of large boxes which fall between the two marked R waves, in this case, 4 large boxes or squares. Now, divide 300 by that number. You should calculate that the heart rate in this rhythm strip is 75 beats per minute. Remember, if the ECG strip is left to run at 25 mm per second for 1 minute, there will be 300 large squares or 1,500 small squares in the strip, indicating a full minute. This is where the 300 and 1,500 formula is derived from. If the R waves do not line up nicely on the large boxes, the small boxes can also be used to calculate heart rate. Similarly, first identify 2 R waves. It can be anyone within the strip. Mark those R waves by drawing a line extending upwards. Now, count the number of small boxes which fall between the two marked R waves. In this case, 19 small boxes or squares. Now, divide 1,500 by that number. You should calculate that the heart rate in this rhythm strip is 79 beats per minute. For irregular rhythms, you will not be able to accurately calculate the heart rate using the R to R interval, as the intervals vary between beats. If you take a longer interval, the rate would become slower. If you take a shorter interval, the rate will then be calculated to be faster. Because of this, we will be counting the number of R waves present in a 6-second strip and multiply that number by 10 to estimate the heart rate per minute. First, you will need to make sure that you have a 6-second strip, which should consist of 30 big boxes. Next, count the number of R waves within this 6-second strip. In this case, there are 7 R waves. Now, multiply that number by 10. In this rhythm, you should get 70 beats per minute. Remember, this rough estimation method should be reserved for irregular rhythms only to maintain calculation accuracy. The next thing you have to know are the inherent rates of different pacemaker size within the heart, which controls the heart rate. By default, the SA node initiates impulse firing, but in the event the SA node fails to initiate that impulse, other pacemaker sites can take over the role, but the inherent rate for these pacemakers will be slower than that of the SA node. When the SA node plays the pacemaker role, its inherent rate causes the heart to beat at a rate of 60 to 100 beats per minute. If the rate falls below 60 beats per minute, this is called bradycardia, while if the rate goes above 100 beats per minute, this is called tachycardia. If the SA node fails to generate an impulse, the role is taken over by the AV node. Its inherent rate is between 40 to 60 beats per minute. When the rhythm is from the AV junction, A rate of above 60 but below 100 is known as an accelerated rhythm, while a rate of above 100 beats per minute is considered tachycardia. Again, if both the SA node and the AV node fails to conduct an impulse, the ventricles will take over the role, but this time its inherent rate is between 20 to 40 beats per minute. A rate of above 40 but under 100 in this sense is considered as an accelerated rhythm, while a rate of above 100 is known as tachycardia. Moving on, we will now take a look at several important intervals and segments in an ECG rhythm. The PR interval is the time from onset of the P wave to the start of the QRS complex. It reflects conduction through the AV node. The normal PR interval is between 0.12 to 0.2 seconds, or between 3 to 5 small squares. For the QRS complex, you will need to determine if the complex is wide or narrow. The normal QRS interval should be 0.12 seconds or less to be considered narrow. Anything more than 3 small boxes is considered to be a widened QRS complex, which could indicate that the rhythm is originating from the ventricles because rhythms propagated by the SA node, atria, or the AV junction will all present with narrow QRS complexes unless there is a presence of aberrant conduction of supraventricular complexes, example, due to bundle branch block, hyperkalemia, or sodium channel blockade. The QT interval is the time from the start of the Q wave to the end of the T wave. It represents the time taken for ventricular depolarization and repolarization. The ST interval, on the other hand, is the time from the end of the Q wave to the end of the T wave and represents the time taken for ventricular repolarization. The PR segment is the flat and usually isoelectric segment between the end of the P wave and the start of the QRS complex, while the ST segment is the flat, isoelectric section of the ECG between the end of the S wave and the beginning of the T wave. The ST segment represents the interval between ventricular depolarization and repolarization. The most important cause of ST segment abnormalities or deviations, for example, elevations or depressions, is myocardial ischemia or infarctions. This is a summary of the important normal ECG intervals which we have just covered. With these basics in mind, you are now ready to move into analyzing and interpreting ECG rhythms.